Hello, this is part 2 of step 17. So we're going to continue talking about different points and segments in triangles. For this video, we're going to specifically focus on the relationships of medians and altitudes. So you may have heard of an altitude before, maybe not a median, but that's okay. A median travels from a vertex to the opposite side, but it actually bisects the side it travels to. So for this one, CD would be our median. See how it travels from vertex C out to segment, or not segment D, out to segment AB, and then D is exactly in the middle of those two segments. So let's go to our special segments and clarify this first. So it goes from vertex to the opposite side and bisects the side. So when you draw these, it's probably easier. We're going to stick with going from B out to AC. It's probably easier to mark where your midpoint or where, so we want to add that in here. So this would be like the midpoint on that side, because segment, bisector, midpoints all kind of fall in the same sort of category. So if I was drawing this from vertex B to AC, let's say the middle would be maybe like there-ish. So it would go from B out to that point, and I'm going to call it D again. And again, there's nothing special about the length of this segment right now. It's just that it has to bisect that opposite side. So the special relationship would be that AD is then equal or congruent. How did I said congruent the first time. So those two pieces would be the same, or we could say CD. It really doesn't matter, but you get the idea, okay? So following in line with our nice organized chart, it follows that the centroid should be the opposite. So if we go back to our notes, or not the opposite, point of concurrency. So the centroid is the point of concurrency of all of the medians, okay? So how this works out with the medians, medians and therefore the centroid, is that when the centroids intersect, it creates this sort of ratio between the segments. So let's go ahead and draw it, and I'll kind of explain how the centroids work. So we can draw again, like there-ish, I don't know, just an estimate. Just make sure they all intersect near the same point, okay? I'm going to call this D. Again, it's really not a big deal. It's a bigger deal that you kind of wait. Oh, wow, that was actually pretty good, my first try. Okay, so these are all medians, so it's bisecting the opposite segment. Okay, so D, let's call this E and F. All of those are medians, so the opposite, or the two pieces that they have now created are therefore the same. So the trick to centroids, oh, I guess we should put the definition when I say. This is the point where all medians intersect. And remember, that point that they intersect is really just called the point of concurrency. Okay? Instead of writing that big term out every time, we can just say where they intersect is fine with me. So the trick of centroids is that where the centroid, all the medians actually intersect, create a ratio between each of the segments. So if we focused on BD for a second, so if I focus just on this piece, okay, it's technically two smaller pieces that I've created by creating the centroid. Let's call this in the middle. Let's just keep it as G like the last video. So if I go from B to G, It's a little different segment than if I were going to travel from G to D, right? They're two different lengths, but they're still part of the same median. So that first half of, or it's not really half, this first part, the yellow part here, has a relationship to the blue one. I know it doesn't necessarily. This one is actually one of my better ones, but this yellow part of this segment is actually 2/3 of BD. So I could say that, I should have done these in order, but it doesn't really matter. BG is 2/3 of BD. Okay, so we have this 2/3, 1/3 relationship. So if you know that it's 2/3 and you want to get to the 1/3 part, just divide it by 2. If you have the 1/3 piece, or you have the blue piece, and you want to get to the yellow piece, you just multiply it by 2. It's kind of the trick. So I can do the other ones too. So if we were looking at AG, well, I'll just leave that there because it's going to erase itself. If we were looking at AF, okay, the 2/3 piece of AF is AG. So AF, the 2/3 would be AG. Oh, I guess I read that backwards. Sorry. AG is the 2/3 of AF, and then therefore CG is the 2/3 piece of CE. Okay, so it's broken up into these different pieces. So let's look at an example, and it'll probably make more sense. Okay, so we know BE is 9, so I'm going to go ahead and label that. Oh, it's the whole segment. So B to E, that piece is 9. And we want to find BQ and QE. So BQ is that piece there. I guess I can go to normal size. It's this piece here. And QE is, we're looking for that piece there. So they're both part of the same median. So by knowing that this is the centroid, we know that it's the intersection of the medians. We could go around and label all of these fun pieces, but not really necessary for the segment we're talking about. So if we look at BE, okay, we want to find each smaller piece. Hopefully you can tell that the bigger piece is the yellow one. It's always going to be the one from the vertex to the centroid. So that piece BQ is the bigger one. This is going to be the 2/3 portion of our segment. And then the blue one is going to be 1/3 portion of the segment. That's kind of what I was talking about with the ratio. So BQ is going to be 2/3. Sorry to confuse you. 2/3 of the whole segment, which would be BE. And QE, I guess I could put that in blue since I highlighted it in blue. QE would be 1/3 the whole segment. So BQ is 2/3 of 9. Okay, which in your head, before you put it in your calculator, 2 times 9 is 18. 18 divided by 3 would be 6. Then same sort of idea for QE. We would have 1/3 of 9. And 1/3 of 9, 1 times 9 is 9. 9 divided by 3 is 3. So our final answers would be BQ is 6 and QE is 3. Alright, I'm going to keep moving just because we can maybe do these in class if we need to. We're already sitting at 9 minutes and I don't want to take up another half hour if I don't have to because of the last video. Okay, so for this one, all we know is that, so it's the same figure. No, it's not the same figure. But P is a centroid. Okay? P equals centroid because we know we have medians. Okay? So we know we have our 1/3, 2/3 relationship. So PT is 2. We are specifically looking for KP, which is that segment there. Okay, so you can do this a couple different ways. If you look at the explanation in the book, it's a super long, complicated formula, and it's really not helpful. Because you can write the segment addition postulates, you can go through all that kind of stuff. But in the shortcut we were just using, if we look at KT as a whole, okay, it's made up of KP and PT. So PT is technically 1/3 of KT, okay? And our goal here is to find KP, which is the 2/3 portion of KT. Okay, so we could do this backwards. Okay, you can do this a couple different ways. You could say, okay, well, if we know that PT is 2, then I can just solve for KT, right? So I can multiply by 3 or divide by 1/3, which way you want to do it. Same thing, it would just be 6 is KT. Okay, which makes sense because then when we plug this in, we want KP. If we know KT is 2/3, or I'm sorry, KP is 2/3 of KT. What's 2/3 of 6? 2 times 6 is 12. 12 divided by 3 is 4. Okay, which makes sense because if PT is 2, and that represents the 1/3 portion of this segment, KP, if that's representing the 2/3, should just be double what PT was, which makes sense that KP is then 4 because all we had to do was double it. Okay? All right, last little bit, we're going to talk about altitudes. So an altitude of a triangle, this might be a term that you're familiar with. It always represents the height of the triangle, okay? So it goes from a segment from a vertex. So it starts at the vertex and goes to the line containing the opposite side, but it's perpendicular is the thing. It's perpendicular to, the opposite side. So if we drew this in a picture, it kind of looks like a median, which is kind of why they're paired together, but it's a little different. So it starts, So it goes from the vertex to the opposite side. But the difference is instead of bisecting the opposite side, it's perpendicular to that side. So vertex to opposite side, and let's just do our upside down T. Actually, I'm going to write it out so you just remember perpendicular to side. So it doesn't matter that it doesn't bisect the opposite side like the median does. So if we were drawing this for B, AC is a nice horizontal line for us. So this would just come straight down like this. Okay, it doesn't have to bisect AC the way that a perpendicular bisector does. So it's kind of a combination of just like being perpendicular, but not adding the bisector portion to it. Okay, so there's no really relationship on, like if I called this point D. BD would be the altitude, but it would not bisect AC or anything like that. Okay, so following in line, the point that contains all the altitudes is the orthocenter. So where all the altitudes intersect is called the orthocenter. So if we go back, point where all altitudes intersect. Okay, so we did the best that we could and we tried to draw this. Obviously mine's not going to be stellar. I guess it should be a little higher, huh? This one's a little harder because of the triangle that I picked, but just kind of do the best you can. Should have not picked it. Something like that. I don't care. You get the idea. Make sure you mark these perpendicular. and I guess we'll just call this G. The only like special relationship of an altitude or an orthocenter is that they can be outside of the triangle, just like the centroid, not the centroid, the circumcenter could be. So that's the only like special characteristic. Can be outside of triangle. Okay, so let's go back. We're going to do one last problem. We're going to actually find the orthocenter in this figure. So it gave us the coordinates of a triangle. First thing we want to do is graph it. So I graphed it. Well, I didn't graph this. This is from the book. I lied. But we can find where the orthocenter should be in a few different steps. So let's start. It wants us to find an equation of the altitude from F. So from F to GH. So I'm going to do my best to draw this and try to make it as perpendicular as I can. Okay, so I'm going to say that is my median, and then I'm going to do the same thing. It wants from G to FH. No. From F. Oh, I drew that backwards. It's okay. And then we're going to go this way. Boom. Okay, so essentially we're trying to find the point here, but if we did not graph it exactly right, let's make sure that we did. So in order to graph an equation of a line, we need a point and we need a slope, okay? Because I'm going to teach you point slope formula, which some of you have seen. I don't know if all of you have seen, so we're just going to go over it. So in order to use point slope, we need a point and we need a slope. Okay, so if we are looking at, so we're doing F to GH, this was our green one, I'll switch colors. So we need a point and we need a slope. Okay, the point, the only point verified on this line is point F, which is -2, 4. And our slope, are not exactly sure where our slope would be. Okay, but we know that it's perpendicular. So we can find the slope of HG. So if we find the slope of HG, we would go up to and over 1. So our slope of HG is up to and over 1. So it would be, there's the bell, would be +2. Sorry about that. So if the slope of HG is +2, and these lines, the green line with HG is perpendicular. Remember, when we change a slope, if they're perpendicular, we flip it and we change the sign. So instead of +2, the slope would be -1/2. Okay? Then from here, our point slope formula is y minus y1 equals m times x minus x1. Okay? From our point, we have an x1, we have a y1, and then remember slope is always represented as m. So we would have y minus 4 equals -1/2 x minus 4. No, I lied. +2, right? Because if it's minus a negative, it would be +2. Okay? Actually, I'm going to write that out so you can see that. So it would be minus a -2, okay, which is really x plus 2. So if I distribute my -1/2, I get -1/2 x minus 1. Add 4 to both sides, y equals -1/2 x plus 3 is our first equation. Okay, so that would be the equation of the altitude, the green altitude. Okay? Then, if we look at the blue one, so we're going to start out the same kind of way. We need a point, and we need a slope. Okay, the only point we know on our blue line is G at 4, 4. And our slope is going to come from FH. So the slope of FH, if we go, I don't know, we could just pick two random points. Let's say up and over. So it would be a -2 slope because it goes up 2 and over 1, but it goes down from left to right. So if we wanted the perpendicular slope of that, remember we changed the sign, so now it's going to be positive, and then we find the reciprocal, so we flip it, so this would be a positive 1/2. Remember our equation is y minus y1 equals m times x minus x1. Here's our x1, here's our y1, and slope is always m. So y minus 4 equals 1/2 x minus 4. Distribute my positive 1/2. 1/2 x minus 2. Add 4 to both sides. Y equals 1/2 x plus 2. Okay, so there's my second equation. Okay, so what I've done so far is I've just created, these are the two equations of the altitudes. The green one is in green that we drew, the blue one is in blue. Okay, so from here I'm trying to find that intersection. So I'm basically going to solve this system of equations. So if these were my these were my two equations, y equals -1/2 x plus 3, and y equals 1/2 x plus 2, we could do this a couple different ways, okay? Notice both y's only have one, what's it called? The coefficient is 1, so those would cancel if we wanted to do it that way. But notice the coefficients on x, one is a -1/2 and one is a +1/2. So if we add these two equations together, we would get y plus y, which is 2y. -1/2 x plus 1/2 x would be 0. And then 3 plus 2 is just 5. Divide both sides by 2. Our coordinate of y should be 5 over 2 or 2.5, however you want to look at that. And then to find x, we can just plug it back into one of our equations. So if I did y equals 1/2 x plus 2, y I know is 2.5. Subtract 2 from both sides. So 1/2 equals 1/2 x. Divide by both sides by 1/2. 1/2 divided by 1/2 is just 1. So our final point, the orthocenter, occurs at 1,5/2, or if you put 2.5, that's fine too. I know that was a very long problem. On the practice, you only have to do one of these, so don't freak out that there's going to be like 17 of these. Okay, then I ended the notes with just all the charts basically, so you can see nicer pictures than ours if yours is not the greatest. Okay, but that is step 17.